Today we are solving LeetCode problem 1536. Minimum swaps to arrange a binary grid. This is a medium-level problem. We are given an n by n binary grid. In one step, we can swap two adjacent rows. Our goal is to make the grid valid. A grid is valid if all the cells above the main diagonal are 0. If it is impossible, we return -1. Otherwise, we return the minimum number of swaps required. The main diagonal starts from position 0, 0 and ends at position n-1, n-1. Everything above that diagonal must be 0. Now let us walk through the swaps shown in this example. First operation, swap row 1 with row 2. Second operation, swap row 2 with row 3. Third operation, swap row 1 with row 2. Now the grid satisfies the condition. Total number of swaps performed is 3. That is the final answer. Now let us understand the intuition behind this approach. Look carefully at the valid grid condition. For row 0, everything after column 0 must be 0. For row 1, everything after column 1 must be 0. For row I, everything after column I must be 0. This means row I must have at least n-1 - I trailing zeros. This is the core observation. Instead of thinking about the whole matrix, we only care about trailing zeros in each row. If a row has enough trailing zeros, it can be placed at a particular position. Now let us establish the trailing zero requirement. For a grid of size n by n, the arranged condition creates a staircase pattern of ones. This means the number of required trailing zeros changes for each row. Row 0 must have at least n-1 trailing zeros. Row 1 must have at least n-2 trailing zeros. Row 2 must have at least n-3 trailing zeros. And this pattern continues. In general, row I must have a minimum of n-1 - I trailing zeros. This is the requirement that each row must satisfy in order to make the grid valid. Now let us formalize the greedy strategy. Step 1. Compute trailing zeros for every row. Step 2. Iterate from I equals 0 to n-1. For each row I, calculate required trailing zeros as n-1 - I. If current row already satisfies the requirement, continue. Otherwise, search below for the first row that satisfies the requirement. If no such row exists, return -1. If found at index j, bring that row upward by swapping adjacent rows. Number of swaps added is j-I. Repeat this process until all rows are placed correctly. This greedy approach works because for each position we pick the nearest valid row. Choosing any row further down would only increase swaps. So this guarantees minimum swaps. Now let us directly go to example 1. First, we calculate trailing zeros for each row. Row 0 has 0 trailing zeros. Row 1 has 1 trailing zero. Row 2 has 2 trailing zeros. So we form an array. 0, 1, 2. Now we process row by row. For position 0, we need 2 trailing zeros. Row 0 does not satisfy it. Row 1 does not satisfy it. Row 2 satisfies it, so we bring row 2 to the top. That takes 2 swaps. Now the array becomes 2, 0, 1. Next, for position 1, we need 1 trailing zero. Row at position 1 has 0. Not enough. Next row has 1. That works. We bring it up with 1 swap. Total swaps becomes 3. That is the answer. Now let us look at example 2. All rows are 0, 1, 1, 0. Each row has 1 trailing zero. But for row 0, required trailing zeros is 3. No row satisfies this condition. So answer is -1. The grid cannot be arranged. Now example 3. Trailing zeros are 2, 1, and 0. Row 0 needs 2. It already has 2. Row 1 needs 1. It already has 1. Row 2 needs 0. It already has 0. So no swaps are required. Answer is 0. Now let us understand the Java implementation. We will first look at the helper function exchange rows. This function is responsible for finding a valid row below the current index and simulating the upward swaps. The function takes 3 parameters. The array dp, which stores trailing zero counts. The integer n, which is the size of the grid. and the integer I, which represents the current row position we are trying to fix. Inside this function, we first calculate the required number of trailing zeros. Required zeros equals n-1 minus I. We also initialize an index variable as -1. Now we search for a valid row below position I. We iterate from j equals I plus 1 until n-1. If we find a row where dp of j is greater than or equal to required zeros, we store that index and break the loop. If after the loop index is still -1, that means no valid row was found. So we return -1. Now if we found a valid row at position index, we simulate bringing that row upward. We shift all rows between index and I one step downward. This is done using a loop from index down to I plus 1. At each step, dp of j is assigned dp of j minus 1. Finally, we return index minus I. This value represents the number of swaps required to bring that row to position I. Now let us move to the main function min_swaps. We first calculate n as grid length. Then we create an integer array mat of size n. This array will store trailing zero counts for each row. Now we compute trailing zeros. For each row I, we initialize a counter to 0. We iterate from the last column toward the first column. If we encounter a 1, we break. Otherwise, we increment the counter. After finishing the loop for a row, we store the count in mat I. So now mat contains the trailing zero count for every row. Next, we initialize ans as 0. This will store the total number of swaps. We iterate from I equals 0 to n-1. For each row, we check if mat I is already greater than or equal to n-1 minus I. If yes, we continue. If not, we call exchange rows with mat, n, and I. If exchange rows returns -1, it means no valid arrangement is possible. So we return -1 immediately. Otherwise, we add the returned value to ans. After finishing all rows, we return ans. That is the minimum number of swaps required. Now let us discuss time complexity. First, computing trailing zeros takes order of n squared time because for each of the n rows we may scan up to n columns. Second, the greedy row shifting in the worst case can also take order of n squared time. So overall time complexity is order of n squared. Now space complexity. We only use an additional array of size n to store trailing zero counts. So space complexity is order of n. Important point to remember. We never modify the original grid. We only work with the trailing zero count array. This makes the solution cleaner and more efficient. This is a classic greedy simulation approach. Important takeaway from this problem. We do not need to physically swap the grid rows. We only need to manipulate the trailing zero array. This simplifies the problem a lot. This is a classic greedy simulation problem. It tests observation, pattern recognition, and careful implementation. If you found this explanation helpful, make sure to like the video. Subscribe for daily LeetCode solutions. And comment if you want the Python or C++ version. See you in the next problem.